and welcome to TLE Eliminators. Today we'll be discussing the solutions to the CP-31 sheet, specifically the 1600 rated problem 27, good subarrays. So let's just dive right into it. Let's go to the CP-31 sheet. Let's pull it up and go to the problem good subarrays. And we're gonna read out the problem, then break it down and see how to solve it. All right. Okay. So you're given an array A1, A2 till AN consisting of integers from 0 to 9. Okay, so the array consists only of integers 0 to 9. A subarray AL plus 1, AL plus 2, so on till AR. So basically a subarray from L and R is good if the sum of the elements of this subarray is equal to the length of this subarray. Okay, so we are going to make sure the sum of the elements of the subarray will be equal to the length. Okay, so R minus L plus 1 of the subarray. For example, if A is equal to 1, 2, 0, then there can be three good subarrays, which is 1, 1, because here the length is 1 and the sum is 1. The other one is this 2, 3, because here the length is 2 and the sum is 2. And also the whole array, here the length is 3 and the sum is 3 as well. So now we need to calculate the number of good subarrays of the array A. And we're given n and we are given some values of A of I and some example test cases, right? So okay, so the problem is pretty straightforward. Problem states that we are looking for let's just summarize the problem so that we have a understanding of what we're looking for. So we're looking for subarrays LR such that the sum AL plus 1 plus so on till AR is exactly equal to the length, so that is R minus L plus 1. Okay, so we are looking for this basically. Okay, and what is the time complexity expected? N goes up to 10 to the power 5 and sum of n over all test cases does not exceed 10 to the power 5, right? So the expected time complexity is like big O of n or n log n, right? Or n root n is also possible, but let's see. The expected time complexity is either big O of n or big O of n log n preferred for this problem. Okay, so now that we have done a preliminary analysis, let's jump right into the problem. Okay, so the first thing we'll do is have some basic orientation, right? So basic intuition. We are dealing with finding specific target subarray sums. Okay, so we are dealing with finding specific finding and counting, I guess, finding and counting specific target subarray sums, right? Subarray sums. So what should be our like base level idea here? So in general, we can think of it in terms of prefix sums, right? So idea, think of it in terms of prefix sums, right? Obviously, when you're seeing the problem, you will go through a bunch of ideas, and you might come across this one. And the reason is simple, right? Because here we're dealing with sums of subarrays. So it makes sense to think about the sum of the prefix minus the sum of prefix at L, right? So for example, for a subarray LR, right, using prefix sums, what is the condition, right? The condition we are looking for is prefix at R, right? We know how to find the subarray sum using a prefix sum, so let's call it prefix at R, or maybe let's write it like this: prefix at R minus prefix at L minus 1, right? Prefix at R minus prefix at L minus 1 should be equal to R minus L, right, plus 1. right? So I guess that makes sense, right? Or what if we want to get rid of this plus one, okay, because it doesn't look very nice in the equation to have, you know, a plus one. So we can, instead of thinking about it as subarrays at L and R which are completely closed, we can start thinking about as subarrays from L minus 1, right? So a subarray from L to R will include the elements P of L plus 1, P of L plus 2, so on till P of R, right? So that's what we'll call half open, half open, half closed subarray, right? So we can write this equation more neatly as simply prefix of R minus prefix of L equals R minus L. All right. Um, yeah. So what have we done so far? So basically, let's take an example. Let's take the example of the array 1, 1, 0, 1, 1. Okay. Now here, let's say we have the prefix sums, right? So the prefix sum is 1 over here, 2 over here, 2 over here, 3 over here, 4 over here. These are the prefix sums, right? So this is our array. This is an example. This is an example. This is our array. And this is the prefix sums which we have calculated. Now in this, so basically any subarray, right? So let's say we find L equals 0, R equals 1. Okay, so L equals 0, R equals 1. And over here, if you take prefix of R, right, minus prefix of L. So assume that it's one indexed and we have like prefix of 0 will be 0. Okay, so prefix of 0 will be considered 0. So this is P of 0, right? And this is P of 1. Okay, so now P of 1 minus P of 0 is equal to 1 minus 0, right? So we can write this as 1 equals 1. So this is a good subarray, right? Similarly, if we want to find another good subarray, we can do something like this. So let's take this as our L, right? So as this is a half closed interval, so we want to check this subarray. So here our L will be 1, right? Our L is 1, our R is 3, right? R is 3. So then we get prefix at we get prefix at R minus prefix at L is equal to R minus L, which is 2. But here we don't get 2, right? We don't get 2. So we get 1 over here. So we can see that this is not a good subarray, right? So this is not a good subarray if we take L equals 1, R equals 3, right? So basically what we have done is we have converted our conditions into prefix sum conditions which we can check via prefix sums, okay? And that's why we made it into a neat equation, because writing R minus L plus 1 doesn't make much sense, because we can just introduce the 0 element over here, right? We wrote the equation in this form, to be neat. And you can write in this form because we can just introduce a 0 element here, right? This is a common technique if you've worked with prefix sums before. And basically what we're doing is we're considering sums which look something like this, okay? So now let's consider this one as well. Let's see, what about here? Okay, let's talk about this subarray. So for this subarray, L equals 3, R equals 5, right? It's half closed, so the left one will be always one more than where the subarray starts, right? L equals 3, R equals 5. So what is R minus L? That's equal to 2, right? 5 minus 3, and this is equal to prefix of 5 minus prefix of 3. So that is equal to 4 minus 2 equals 2, 2 equals 2, right? So we can say that this is a good subarray, right? This is a good subarray. In total, all the good subarrays is this, as well as this and this. That's why the answer to this test case is 6. Okay. So this is what we have understood so far. The question, and we have converted into a prefix sum form, right? Simple prefix sum condition on the question, and we have understood how an example works. Okay, so our next task is to lower the time complexity, right? Because even if we find the prefix sums, we cannot go through all L and R and check which are satisfying, right? We cannot do n square because n goes up to 10th power 5. So we cannot do an n square solution as n goes up to like 10th power 5, right? So we need to find some way to optimize this. Now, one of the ways which we optimize prefix sums or DP problems is by considering the equation that they form. Okay, we need to consider the equation that they form, and this helps us somehow sometimes optimize DP states or prefix sum states. Okay, so here when we write P of R minus P of L equals R minus L, one of the reasons we wrote it in this form is because it's very nice and symmetric. Okay, it's very nice and symmetric, and we can now simplify this. So if you rewrite these equations, we get P of R minus R, right? So if P of R minus L equals R minus L, then this equation also holds, right? P of L minus L, right? This equation also holds. Now basically what we're getting is, every time we get some P of I minus I is equal to some P of J minus J, we have a valid condition, right? We have a valid condition. We can simply bring this to this side and then we formed a valid condition. So basically what we are in essence are doing is counting the number of pairs with equal value of P of I minus I. Okay, so I'll show you an example using the previous example which we had. So let's say we had our array was A equals 1 1 1 sorry 1 1 0 1 1. Okay, this was our array. Now let's make the prefix sum array. So it will be 0 1 2 2 3 4. Right, now let's make the values of P of I minus I. So that's going to be P dash, let's call it P dash, and that will be 0 minus 0 is 0, 1 minus 1 is 0, 2 minus 2 is 0, 2 minus 3 is how much? 2 minus 3 is minus 1, right? 3 minus 4 is again minus 1, and 4 minus 5 is again minus 1, right? So now basically we are saying we're counting the number of times or the number of pairs which can which have an equal value of P of I minus I, right? So as you can see, these three have equal value of P of I minus I, and these three also have equal value of P of I minus I. That means that anytime we pair any two of these up, we should get a valid subarray. Okay, we should get a valid subarray. So the number of pairs we can form, what is the formula for pairs? Number of pairs by combinatorics. The formula of number of pairs is simply n choose 2, right? Or basically n times n minus 1 divided by 2, right? So for each different value of P of I minus I, we need to see how many pairs we can form. So then for this, it will be 3 values. Since there are 3 values, so n will be 3. It will be 3 times 3 minus 1 divided by 2, which equals 3 times 2 by 2, which equals 3, right? Similarly, how many pairs can we form this way? We can form again 3 times 3 minus 1 by 2, or 3 pairs. So the total answer will be the sum of these, right? Total answer will be sum of these. 3 plus 3 equals 6, right? The answer will be 6. And this matches with the answer we saw earlier. Manually we calculated that the answer for this test case is 6, right? And the reason for this is simple. Yeah, and we can see that this condition is equivalent to having P of R minus R equals P of L minus L. So basically we just need to see how many times this gets satisfied, right? So that's what exactly what we're counting. How many values of P of I minus I have the same value, and we're pairing them up, right? Because each pair is a different pair of L and R which satisfy this equation, right? So that's exactly what we're doing using some combinatorics. So then this gives us a fast and clean solution to the problem. And what is that solution? The solution is simply solution, right, for each I, for each I. So for the first one, as we see, we introduced this extra prefix of 0, right? So this also should be calculated. So we'll just note that down. So first we'll create a map, right? Unordered map or map, either way. If you use a map, you'll get a log factor. If you use an unordered map, you won't get a log factor. So we can have a map, empty map, and also we can map, let's say, from int to int, right? And we can also set the map of 0 as 0, as map of 0 as 1, right? Or map of 0 plus plus, because we have seen the value 0 minus 0, right? The prefix sum is 0 and the index is 0, so we have to count that. All right, now for each I, for I goes from 1 till n, what we have to do is we have to find the prefix, right? So we can have a prefix sums. So basically the map of prefix of I minus I is incremented, okay, because we are counting how many particular values of prefix of I minus y exist. Okay, now all we need to do is go through all the map values. So for x and y inside the map, right, for x and y in the map, y is the number of times a particular value x occurs, right? Y is the number of times a particular value x occurs. So we can make about y times y minus 1 by 2 pairs, right? We can make y times y minus 1 by 2 pairs. So we add that to our answer, and then finally we can return the answer. Okay, we can return the answer. So this is the full solution to the problem. We have to create a map to count how many unique, like how many times the values of prefix of I minus I get repeated. Each time we have potential pairs of prefix of I minus I with the same value. We pair them up and we count how many such pairs can be made, right? And the reason we arrived at this solution is by thinking of prefix sums, since it is natural to think of prefix sums in subarray problems, and we rearrange the prefix sum equation to be nice and symmetric, right? So it is also a lesson in looking for symmetric patterns. Okay, what is the time and memory complexity of this solution? So the time complexity is obviously big O of n or big O of n log n, depending on whether you use map or unordered map, right? So this is for map and this is for unordered map, and the memory complexity is big O of n, right? So that's pretty much it for the problem. And the topics here are, I guess, basic prefix sums, very basic combinatorics for the pair formula, right? And I guess simplifying equations, although that's not exactly a topic, but yeah, knowing how to simplify equations for symmetry, I guess, right? That's just a broad idea, not a topic exactly, and broad idea, right? This is helpful in like several like DP problems when you want to simplify your DP state and count how many times a particular state occurs, basically. Alright, so that's about it for this question. Let's have a quick look at the code, okay, to know exactly how to implement it. So yeah, I define n and the input is a string, so that's why I'm taking it as a string. Pay attention to the input. We are using an unordered map so that the time complexity remains big O of n. We increment map of 0 because 0 minus 0 also must be counted, right? Because basically our L and R are half open intervals, right? L and R are half open intervals. So each interval is basically mathematically something like this, R comma L, like this, right? So that's why we need to consider L equals 0 as well, right? So we write map of 0 plus plus. Okay, here the prefix value stores the prefix. We don't need to make a prefix array because we only care about the current value of prefix, so we're just directly having one variable for it, right? We are increasing map of prefix minus I plus 1, right? So we are counting the specific value of prefix minus I. Then here for the final answer, we're counting how many pairs we can find of same values of prefix of I minus I. We just use the normal formula y times y minus 1 by 2 for NCR pairs, right? NC2 pairs. And finally, we print the answer. This is a short and simple solution to the problem. Of course, there exist other solutions, including some nice solutions with DP or etc. strategies, right? But this is the most straightforward solution to the problem, as well as the one which has been discussed in the editorial. All right then, thank you for watching. Hope you learned something. If you are stuck at any step of this implementation, do rewatch the video. If you are unable to think of how you would come up with this kind of transformation, just keep in mind that we are trying to bring all R terms to one side and all L terms to one side, and this is a common trick in DP or prefix sum problems. All right, thank you for watching and see you in the next problem.